Hello everybody and welcome back. It's Root Beer here, and I'm going to finish up the 2015 Friar contest today. So that's the grade 9 written contest as opposed to the Pascal, which is the grade 9 multiple choice contest. So we've come a long way. We've done questions 1, 2, and 3. You can check them out in previous videos. I'm sure they're on the link on the side for YouTube in sort of the suggested videos. But we're going to be dealing with question number 4 today. So let's take a look at that question. Hopefully you've given a little bit of a go at this question before we start, so you get a little bit of the sense of the question. Even if you weren't able to solve all of it, hopefully you at least looked at it and tried to work it out. It's always for the best. So question number 4, the token, which is just the LaTeX bullet point, because I'm pretty sure they use the LaTeX word formatting program. So the token black dot is placed on a hexagonal grid as shown. At each step, the token can be moved to an adjacent hexagon in one of the 3 directions: up to the left, straight up, or up to the right. So you can go up, you can go over, you can go up and over. The token can never be moved in any of the 3 directions that are even vaguely down. So down to the left, down, and down to the right. Okay, so part A. What is the minimum number of steps required to get the token to the hexagon labeled A? So this hexagon up here. There's a C hexagon. I'm surprised there isn't a B hexagon anywhere. So minimum steps to get to A. Alright. So usually in these videos I will reproduce any diagrams that they show, but I think you'll agree there's a lot of hexagons here. I don't want to be reproducing this. So we're just going to stay here with our trusty mouse cursor. If you're not on a resolution that's high enough to see that, that's okay. I will be writing down my thoughts, but for the playing around, download a copy of this contest and try and solve A yourself. See if you can do that. But I'm playing around here. How can I get to A? I need to at least get to A before I start trying to minimize it. So if I go 1, 2, 3, 4, 5 of the up to the left directions, I lie right below A. Then I go up, up, up. Okay. So that's what? 1, 2, 3, 4, 5, 6, 7, 8, and I'm at A. Okay. Can I do any better? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that's way too much. 1, 2, 3, 4, 5, 6, 7, 8. Alright. 1, 2, 3, 4. Oh, we've gone too far. If I go straight up by 4 of them, I'm too far up. I will never get back down, even if this hexagon were here. Okay. Now, it's all well and good to experiment, but likely we're going to have to get some math in here. So, what I've noticed just from playing around a little bit is that these steps are not equal. Other than in terms of moving left and right, the up left and up right arrow movements are essentially the same. They basically accomplish the same goal. They're mirrors of each other. And I'm noticing that they go up half a hexagon overall. We can only go up. It's just, are we going up to the side or are we really going up? So both up left and up right go up about half a hexagon tile. Right? So if we start at this dot and we go up left twice, we're at sort of the same level of hexagons as if we'd just gone straight up from the beginning. So what does that tell me? It tells me that going up is faster. We cover more height. We might not cover more left, right, side to side distance, but we certainly cover more height. And A is really high up. So we want to use the up arrow as many times as we can. Another thing I'm noticing is if I go up left and up right, that's the same as if I went up right and up left. Okay? So there's probably going to be lots of different ways to use this minimum. And I'm pretty sure the minimum is going to be 8. We can go up, up, up 3 times. We can use the super up, the up operation 3 times. And then if we go any further, we're way too high, and we got to use the up left operation to complete everything. But we never do any side-to-side backtracking. We never, we never use half a height when we could be using a full height. So I think it should be 8. 8 should be our answer. Then to get to A, we need 5 up lefts. Alright, so we need a total of 8 moves, and that should be the minimum. Alright, so B part. I'm going to need that diagram. With justification, determine the maximum number of steps that can be taken so that token ends up at A. Okay, so we're still using A. I think they could have moved it and made it a B and put it somewhere else, but that's beside the point. So, want to determine the maximum number of steps. Well, using that up, I mean, if we use the up from, say, from the very first move, we could do that, but I mean, we could go up left and up right, accomplish the exact same thing and take 2 moves rather than 1. But how are we going to figure out the maximum number of steps? Well, we can at least note that we need to minimize Remember, I defined h on the other side as the height of a hexagonal tile. So we do not want to go straight up if we can help it. You know, this notion of h, this height of the hexagonal tile, that actually might be the key to solving this. Not in terms of any left and right stuff, but how high, how high up is A from the dot? Because it seems like the left and right, the up left and the up right, I mean, we could probably just go back and forth, back and forth, back and forth, so left and right probably isn't a consideration. Notice that if I go up to the left, 1, 2, 3, 4, 5, I'm right below A. So I can definitely get over to the column that A is in certainly, before I can get up to the height of A. So I think height is our priority here. I could be wrong, and maybe we'll have to introduce a notion of hexagonal width, but I think we should be focusing on height. So I may have to reproduce a little bit of the diagram here. I do apologize, I'm not very good at the hex stuff. Drawing hexagons is really hard. So I know I go up to the left 5, and then I can go straight up 3, because the minimum distance should be 8 unless I'm just discovering something new right now. So is that the dot? 1, 2, 3, 4. No, I need one more. Dot 1, 2, 3, 4, 5, 6, 7, 8. So that should be it. So A is up here, and our dot is down here. What is this height? 1 hexagons, 2 hexagons, 3 hexagons, half a hexagon, so 3.5, 4, 4.5, 5, 5.5. So 5.5 hexagons worth of height. Okay, we're trying to get rid of these ups. We're trying to use the side ones. So no matter what operation we use, every time we're at least going up half an h. Half an h. Okay, we can't help it. We could go up a full h, but that'd be going a little too fast. We have to at least go up half an h. So if we divide this height by half an h, we should be able to know sort of the maximum number of steps we can take. Maybe we can't get that, but at least we'll have an upper bound. So 5.5 divided by 0.5 should be 11 moves. So any more, and we'd be higher than A. Now, it might be that we can't fit in the up left and up rights, and we will have to use an up arrow. But maybe we can use... actually, I think with serendipity, we actually have enough to do it here. So 1, 2, 3. If we can get just a path of 11 to A, we're done. 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that's nice. I was going to fill out the whole thing, but then I realized I didn't need to fill out the whole thing just to get the height. But apparently I filled in enough. I guess my brain was working a little subconsciously there. and had already solved the problem for me, but wow, okay. So we went up to the left 5 times, then to the right, then to the left, then to the right, then to the left, then to the right, and then to the left. Now, before I go back and double check that there weren't any holes in the grid and that the path I just laid out doesn't actually exist on their diagram, notice that it wasn't enough to just say we could have a maximum of 11 moves. We need to show that maximum was achieved, because maybe there wasn't enough space in the diagram to actually do it. We would have to resort to 10 or something. Now let's just double check. Can we do that on their actual diagram? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and we justified why it would need to be 11. It couldn't be any more, otherwise we'd be way too high. Okay, C part. I don't know why I keep scrolling down. I'm probably going to need this diagram. Okay. So we haven't used this token, this letter C yet. We're probably going to use it and maybe A. C part. Using exactly 5 steps, the token can end up at the hexagon labeled C in exactly 20 different ways. Using exactly 5 steps, the token can end up at n different hexagons in at least 20 ways. Alright, so 5 steps we can get to C in exactly 20 different ways. Using 5 steps, the token can end up at n different hexagons in at least 20 different ways. So we could get there in 20 different ways like we did with C, or maybe we can get there in 40 or 50 different ways. But the point is, with exactly 5 steps, we have at least 20 different types of moves that we can get to n different hexagons, determine with justification the value of n. Okay. Not the most nicely worded question, but I'm pretty sure I got what they're getting at. So to get to C, we can go, using exactly 5 steps, we can go 1, 2, 3, 4, 5, or we can go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, things like that. So we have multiple different paths. They're wholly unique to get to C. How many other tiles out here in exactly 5 steps do we have that many choices for the ways we get there? We have 20 different paths to get there. Still just using the up, left, up, and up arrow moves. Still can't move down. Okay. So, I think back in A, I mentioned that going up to the left and up to the right is the same as going up to the right and up to the left. So I think that might help us. So the order of our moves, if we go up left and up right, that's the same as going up right and up left. We don't end up at different locations. And to prove that, we just need to show. So that's up, left, up, right. So we get to the exact same tile as if we had just done up right, up left. So we have two more cases we need to showcase. We need to show that they both interchange with the up operation. So up to the left and straight up. Well, that's the same as if we went straight up and then up to the left. Feel free to try these on your own. If you download a copy of the contest, you'll have the little hexagonal grid that they have. And what's the last one? We start at the dot, and we move up to the right, and then we go up. So that's this one, and up, and that's up and over. So all we need to do is say things like, okay, how many different ways are there to get to the hex that is exactly 5 tiles above the start? So going up 5 times. Or how many different ways are there if we're going to go up twice and up to the left twice and up to the right twice or once? Right? We need 5 moves. So we're going to use sort of coordinate notation to keep track of everything. So we can have 5 of the up to the lefts and nothing else. It's not going to allow for much variability, but it's still 5 moves, and the order doesn't matter. We're going to write down a big long list of all possible ways to get 3 non-negative numbers to add up to 5. When you're doing lists like this, it helps to be very methodical. So this is looking like it might be a lot of work, a lot of cases. 1, 4, 0, 1, 3, 1, 1, 2, 2, 1, 1, 3, and then 1, 0, 4. And lastly, if we have none of the up to the left moves, Okay, that's all of them. So we worked through it very methodically. We just sort of decreased. We put our biggest numbers. We put the biggest number possible to start off with the upper lefts, and then we slowly took off of him, keeping our biggest number with the ups as much as we could, and then slowly taking off. Then we filled it out rather methodically. Notice that there's 1 with 5 here, 2 with 4, 3 with 3, 4 with 2, 5 with 1, and 6 with the 0 here. Okay, so that suggests that we probably did it right, because there's a nice sort of pattern with what we did. All right. So how can we arrange these moves? Well, there's a way to calculate the number of different ways to rearrange sort of letters that have been with duplicates. So if we have A up to the lefts, B ups, and C up to the rights, this is a sort of a combinatorial problem. So we add up how many there are, which will always be 5 for our purposes, but I thought I would just give the general form here. So this is how many different ways. Right? If we figure out the number of ways we can rearrange our moves, that tells us how many paths we have. Because remember, the final token, the final hexagon we land up in, doesn't matter. It doesn't matter the path we took. It matters what moves we're using. So once we know that we're going to be using 3 up to the lefts and 2 ups, we know what the final hex is. None of our different paths are going to change that. It's just all about, do we go up first and then we go up to the left, or do we go up and up, or do we go up to the left, up to the left, up to the left, up, that sort of stuff. That's all that matters, and that tells us the number of different paths. Well, the number of different paths is exactly the number of ways we can rearrange the 5 total objects, the up to the left, the ups, and the up to the rights. So as we'd expect, if we have 5 up to the lefts, we can't really rearrange those. You're always going to have the move up to the left, up to the left, up to the left, up to the left, up to the left. So there's exactly one way in 5 moves to get to that hex. There are other ways to get to that hex, sure, but they don't involve using exactly 5 steps, and that's what the problem's asking us for. So I will write out the formula for the first few, but after that I think I'm just going to write down the final calculations. I don't want to take up too much of your time or my time. But let's just see how it's used. 5 factorial, that's 120 divided by 24, 1, and 1. Going to get 5. So 5 factorial divided by 3 factorial, that's 120. Divided by 6, that's 20. divided by 2 divided by 1, that's going to be 10. So, using 3 up to the lefts and 2 ups, there's 10 different ways to get to that final hex. So that's 120 divided by 6, that's 20. So we have final answer 20. So this one is one hex that we can get to in at least 20 different ways using exactly 5 moves. We'll use 3 up to the left, 1 up, and 1 up to the right. And if we look at our diagram, the one we were given, 3 up to the left, 1 up, and 1 up to the right, that's sort of the mirror image of C in this dividing line. Okay, so we can sort of see that this is working. Eventually, one of them, 3 up to the right, 1 up, and 1 up to the left, will get us back to hex C, which we know is definitely 20 different ways. So that's sort of a little check we can put on the method we're employing. (302), well, that's just going to be 10 again. It's the exact same formula up here because products commute. 230. There's another 10. 221, that's one we haven't seen before. So let's actually write that one out. 2 factorial, 2 factorial, 1 factorial. So that's 120 divided by 2, which is 60, divided by 2, which is 30. So here's another one. Going up twice, up to the right once, and up to the left twice, we can get to that hex in 30 different ways. So here's another one. Also 30 different ways. Up to the left twice, up to the right twice, and using the up operation only once. I think all the rest of these calculations we've seen, they're just rearrangements of previous formulas. So there's another one. So we have 1 on the previous page. Now we've got 3 more, so we've got a total of 4 going. So this one is C. Sorry, C is somewhere else. Sorry, this isn't C. Jumped the gun a bit there. This one here is C. Up to the right 3 times, up once, and up to the left another time. So I think we got 6 so far. There might be a couple more. Actually, no, I think that's it. 0, 1, 4. And finally 0, 0, 0, which brings us all the way back to using the up to the right operation 5 times. There's only one way to rearrange those, so only one path to get to that hex. Alright, I think that was it. I don't think we were asked to label them anywhere. But we'd have this one, we'd have this one. I think this one up here is definitely one. 1, 2, 3, 4, 5, 6. I think that's them right there. So 1 C, and then up to the left of C, and then down to the left of C, and up to the left, and then the mirror image of C and up to the right. I'm pretty sure that's them. 1, 1, 1, 2, 3. 1, 2, 3, 2, 3. And 1, 1, 1, 1, 1. Yeah. So that's going to be those 6. Alright, we've figured out exactly how many different hexagons can be reached with exactly 5 steps in at least 20 different ways. So it was quite the question. We had to rely on combinatorics, and if you haven't seen combinatorics, if you haven't seen those factorial formulas I have used, I suggest you look online and try and brush up on them. I'll see if I can make some videos about them. Combinatorics come up every now and again. They're more common on the more senior papers, but they can be very helpful with the grade 9, grade 10 ones as well. A good starting resource would be to learn more about Pascal's triangle if you don't already know about it, because Pascal's triangle can very easily be related to this same sort of stuff of how many different ways can we get from here to here using very specific methods. So I would look up Pascal's triangle, and I'd Google search Pascal's triangle and movement, or look for another video of mine or somewhere else online, or read solutions to the previous contests. There are a bunch of online resources you can go to if you're having trouble with combinatorics, if you're just not familiar with it. But definitely relied on combinatorics in this one. So certainly a useful branch of mathematics that you might want to be familiar with if you're taking these contests seriously. But other than that, that's all for me, and that's all for the 2015 Friar. So join me again in another video for another contest at another time. It's been wonderful having you guys here, and I'll see you later.